happy Thanksgiving weekend. I know it's kind of weird having Thanksgiving in October, but I am from Canada. I'm actually came and flew down from Toronto originally, just because I really wanted to show you about a lot of diagrams of arrows and boxes and talking about architecture, because it's something that we don't talk about too much. Yes, we should. And basically, as systems grow bigger, they get complicated. So at the very start of the project, we're super happy, high-fiving. Yes, we've just made our first sale. We raised our first round of funding. Or maybe these are the people before you joined where they're super, super happy. And then all of a sudden, God damn it, I need help. I can't manage this code base. Everything is going wrong. I can't make heads or tails of it. We need help. And basically, these are some slides from Jason Gorman. And as a project continues on, productivity just plummets in a lot of projects. And guess what? The cost skyrockets in payroll, and this is very unsustainable. This kills companies. This is something that you need to keep the check of, and it's all about developer velocity. We want to maintain developer velocity over time. So what happened? Well, too much knowledge is required to make simple changes. Our simple system is no longer simple. You have many people working on many parts of the code base, basically stepping on each other's toes. I'm sure everybody in this room has been in this situation at least once in their lifetime. So what can we do? Well, it's all about building high cohesive systems that are loosely coupled. So the goal of software architecture is really to minimize the human resources required to build and maintain a required system. So what we really want is we want to build a bunch of Lego blocks so then we can build amazing structures like the CN Tower. So first, let's talk about what our app might be today. So many people use, whether it's Django, Flask, Rails, you name it, a lot of MVC frameworks. I know some of them are going to be called MVC. Some of them are multi-view, presenter. I'm just going to call them MVC just to make life easier for myself. And if you think about it, you got a client, the top layer, you have that controller view layer, and then you have the model layer, usually some kind of active record pattern, which is your ORM, and then you talk to the database. And as things grow, you should be like, all right, where the hell do I put all my logic? So you really have two choices that people talk about. You got fat controllers or fat models. And unfortunately, neither of them really work. So someone comes along and says, you know what? You need a service layer. So let's put all of our code somewhere in the middle. And if you think about it, you have your controller, service layer, model layer. You basically recreated an enterprise pattern that's been around for 30, 40 years called layered architecture. And specifically, you're most likely following open layered architecture where each layer you can actually access. There's no protection between them. And that kills your project. I don't know how many times I've seen code where it goes through some kind of business layer, but then the controller just decides to talk to the model directly and save to the database and basically bypass all the security rules. What we probably would rather do is the closed layered architecture, where it's that same MVC, but this time we basically only depend on the layer below us, and you cannot go and jump layers. So we, again, want a very, very small presentation tier. We don't want a fat presentation tier. No one likes to get fat. We want all of our logic to be right in that middle. And then we want the data layer to be pretty simple, because we're not really programming databases in enterprise web apps. What we're doing is we're programming behavior, and we actually don't want to be tied to our databases. But we still have a problem. And that is that everything still depends on the data layer. We really haven't changed much. We just moved the code around. And now we still have to figure out, okay, how can we get rid of the dependence on the data layer, which is really an infrastructure concern. So let's do some thinking. And is there a concept that you learn very, very early on in some software theory that could actually help us with this problem? And as we write code, we learn to write modular code because it's easier to read, easier to maintain, and we really have smaller units of work. But we still have the dependency problem where instead of having one huge 1,000-line function, now we have a bunch of classes all over the place, and they all still depend on each other. So we can have either implicit software dependencies or we could have explicit software dependencies. An implicit software dependency is that in the code, you just directly create the model or the relationship that you want. An explicit one is that you actually pass it in, and I'm going to name that more or less dependency injection, where the two most common ways of doing an explicit dependency is either through the constructor when you construct the object or through a setter. Sometimes you have to use the setter because the framework that you're using just won't allow you to have access to that constructor. And this allows us to, at runtime, specify what our dependency is. So I could have a booking manager system. So my example here is basically a clone of an Airbnb booking system, rental property system, where the booking manager has a method called process payment, and that's directly hooked up to a Stripe implementation. But that's still not really what we want because we're still dependent on Stripe. We're still dependent on our database models. And this is where polymorphism comes in. So polymorphism is the whole, if it walks like a duck, if it talks like a duck, if it quacks like a duck, it's probably a duck. So we can use polymorphism, and what we can do is we can actually invert the dependency. So we actually can move the dependency management in this diagram to the left by introducing an abstraction. And what we want to do is we want to program to these very, very stable abstractions. And what a stable abstraction really means is that something that does not change frequently. So what we want to do is we want to isolate the code that we're going to be working on over and over and over again. Maybe we're changing an algorithm to be more performant, but that does not change the behavior of our system. And that's really what we want to focus on. So here in the diagram, you can see that we actually created an interface that has one method called process payment, and then we have multiple. We have like a Stripe implementation, we could have a PayPal implementation, or even a testing fake implementation that we can run our tests faster, where we can actually run end-to-end unit tests that are collaborative, where we don't actually have to depend on a web call. So here's some examples of actual Python code, because it is a Python conference. I thought some Python code would be nice. So I believe in type checking. I also believe that typing really does solve a lot of problems. I do know that you can do implicit typing, which is basically, again, the whole reason why Python is duck typed in the first place. But I find that you can't trust that, especially as your application grows very well, because then you end up, the only way you can trust is by doing a lot of testing. And sometimes it's just easier to do this part of your CI process. So on the left-hand side, I have structural typing. So here we're doing typing through using a mixin or through inheritance. And then on the right-hand side, there's a way of doing kind of nominal typing, especially in MyPy, and that's more of, you still get the type checking and you still get duck typing where you don't have to do that inheritance chain. I personally think inheritance is the devil. I'd prefer composition. But you do have a little bit of a runtime cost. And these are just two ways that you can actually create this interface, this abstract interface, and the implementation that goes with it to break that dependency. So let's go back now. So we know at the code level, we can invert our dependencies and we can program to standard stable interfaces. Could we do that with the layers? And yes, we can. We take our original, on the left, layered architecture, and we can actually invert the dependency of the data layer up towards the business and domain layer. And I don't know about you, but this has a name. This has many names, actually. So we have hexagonal architecture. Some people call it the onion architecture, clean architecture, or ports and adapters architecture. And the whole idea is that instead of pointing down towards your data layer, data flow still goes that way. We actually point inwards, and we have a very simple rule while we're developing is that the domain layer or your business layer is nothing but plain old Python objects, plain old popos. And all the dependencies have to go inwards, and the inner code cannot depend on anything on the outside. And this is basically, as you grow your application, you have to, again, change a lot of infrastructure code. Your infrastructure code actually changes usually more often than your domain code. And this way you don't have to rewrite your application every time you change what database schema you're using. Here's just another diagram. As I mentioned, clean architecture. This one's more of a circle. And you can see that on the left-hand side is a slice of a cone where the very middle is your abstract, general, rarely changed. That's where your business rules are. Again, plain old code, nothing special. And then the very outside is the part that really changes all the time. And this is how you can isolate those changes. And again, not have to rip all your hair out while you're building a system. So let's talk about a little bit of those layers internally. So we have the entity layer, and this is really where your main models live. And this is where like domain-driven design can really, really help. I'm trying to keep it really DDD light for this talk because I could bore you forever for DDD. And in terms of DDD, you basically have inside of this layer, you have also entity models. I know it's confusing because it's the entity layer, but you have entity models, value objects, domain services, factories, and aggregate routes. I'm going to go through them like a lightning talk. So first, we have value objects. Wouldn't it be nice if we just use very simple data types to actually do attributes on our objects? So we know how we use strings, we know how we use integers. So when we change an integer on an object, we don't like mutate it. We just throw the old one out and put a new one in. Couldn't we do that with data objects that are more complex, that provide meaning? So I have here value objects. So value objects have no identity. They do not exist on their own. And the best way to use them is by creating immutable objects. Data classes that have frozen keywords, awesome, because you have a runtime check to make sure that you can't modify this in Python. So this is just a simple way of describing a class. And again, sorry, not a class, an address, but the address is now treated as one variable that you change in a get-go. Then we have entity objects, and an entity object has two special properties. One, it has a lifespan, so it changes over time, and two, it has uniqueness within your system. So in this example, I have a rental property, and a rental property can change its availabilities. It can be booked, it can be unbooked, and we use value objects to also help describe entities, and entities can actually have an object graph to other entities. But when you're designing your entities, what you really want to avoid is anemic domain models. Every single person, including myself, especially when I'm prototyping, I'm not going to do a domain model at the very beginning. I'm just going to do very much a transactional script where I'm going to have a data object, and then I'm going to have a bunch of code that changes that data object, which if the app is very, very simple, that is the right approach. But over time, that model, you spread all your logic everywhere around. I'm going to show an example in a second, and you bleed, you cry, and you just sweat, and your life is a living hell. And it's just sometimes worth creating a rich model from the very beginning. So here's an anemic model. I tried to keep it really simple. Hopefully it's not too simple. So we have a renter object, and the renter object is just like a data class, but it mutates. And you can see that all the logic is in some other method. Like you're fetching the renter, and then you're changing the address from a web request. And what ends up happening is that every single client of your code re-implements logic, and now you have and places where you have to figure out how the code works. And it's even worse where sometimes people push this logic to the client, which could be a JavaScript app. Now your JavaScript app has to figure out what parts of a renter are you changing. Are you changing their contact information? Are you changing their billing information? Because the model itself does not know. And unfortunately, anemic models come a lot when you're using ORMs because we don't actually put methods on them to actually help them manage themselves. So we're kind of breaking that classic OOP theory of you have methods, you have command methods that change internal state. So this is a rich domain model. The only difference here is we actually have a method called update address, and this is where the object can change itself, and all the logic lives in one spot. Even better, you can use invariants. Invariants are just a way of protecting yourself, where if a programmer tries to use your object, you throw an exception. Your code should never get here in production. This is more of something to catch an error from the very beginning, or you can use descriptors. And domain services are just code with no state that helps your domain model. Now, the biggest thing that I want you to take away is the aggregate root. That is your unit of work, and that's what you fetch from the database. And that's what you're going to actually save in the database, so that's what you hydrate. In this example, we have two entities. We have a property owner and a rental property, and these are also aggregate roots because this is where our operations are going to be, and these are going to be the resources in our RESTful API if we go that route. But what about the database? How do we keep that simple? Well, the repository pattern is, again, a way of abstracting data where we can use Elasticsearch, Postgres, Mongo, and the aggregate root is perfect for NoSQL because usually it can be a document. So here's just a way of defining it. You just have simple CRUD methods, and you implement them depending on what your backend is. And this is just an example of how you can call from a Django app and API view to create that web tier facade to actually call into your code. Another best practice is using data transfer objects between layers because you don't want to leak abstractions. Do you do this all the time? Not really. It's really if you need to, if you want to protect your layers. And this is just a DTO example. Data classes are great for that. And you can see here that I have the same components in all three architectures. The first one's layered. Then I have component-based, hexagonal-based, and hybrid. And I just moved around the components, but the same components exist everywhere. And this is just a way of organizing your code. And a great way of thinking about doing unit tests is you want to test behavior, and you want to test the behavior of a component, and you want to keep all the inside messy so you can change it without having to rewrite all your tests all the time. One thing I hate is test maintenance, and people do too much testing or no testing at all. So in this case, you would only test the things that are not grayed out, and it makes your life a lot easier. And that's just talking about that. And you want to use collaborative unit tests, want to reduce mocking as much as possible. If you're going to use mocking, inject it. Don't just monkey patch it, or duck punching, as it used to be called. And do I always follow these rules? Well, it depends. If I'm building a very simple microservice CRUD app, I probably won't follow these rules. If I know I might have to change the database because I need to do optimizations, maybe I will do the request layer and the domain layer as one unit, and the database will switch with a repository pattern. Or I might even invert that the other way, where I might never switch the data layer, and I'm only changing what calls into my application. And the whole point is by really simplifying where the code changes, and we keep it in one spot. And that's all I have, so thank you.